Introduction. In this module, we will discuss aspects related to drawing office orientation. We will look at the history of drawing, personal attributes that a draftsperson requires, the drawing office, and communication within the drawing office. We will also discuss what modern technology is used in the drawing office and how it is used. History of drawing. Through the centuries, man has tried to portray the way of life and customs of his time through pictures. Thus, the first drawings had primarily a historical background and were an attempt to depict the national pattern of life, morals, and traditions, so that the future generations could learn about the development of a particular group. The pictorial message was often represented so effectively that no words were required to elucidate a specific aspect of national life. Naturally, we associate the first drawings with national art, and drawing as such is understandably seen as the work of the painter or plastic artist. Now, what is a plastic artist? Art forms which involve physical manipulation of a plastic medium by molding or modeling, such as sculpture or ceramics. So now, this interpretation of a drawing, namely that it should be a picture, is still held by many people, and even when the pure pose and nature of the technical drawing is explained to them, the drawing remains a pictorial image as far as they are concerned. So some of the things that you should note here is the cardinal difference between a technical drawing and a picture is important. The first is aimed at the implementation of an instruction for the realization of a practical goal, while the second primarily provides aesthetic enjoyment. A characteristic of the earliest drawings was the absence of dimensions, according to which the precise size of objects could be determined. All impressions of size are merely determined relatively by juxtaposition as a criterion to the size of a man or animal next to the other detail. In this connection, one remembers the work of Albrecht Dürer, one of the greatest of erstwhile illustrators, who was born at Nuremberg in 1471. Mention should also be made of the magnificent illustrations of the human body made by Vesalius in his De Fabrica Humana Corporis, a work on medical surgery published in 1543. Some of the early uses of drawings for more practical purposes appear in architecture, and there's a stone tablet in the Louvre Museum in Paris on the lap of an image of a Babylonian governor on which the basic plan of a temple at Ningushi is chiseled. And an interesting phenomenon in connection with the basic plan is the provision of a scale as part of the plan. Thus, the drawing is immediately placed in the category of a workman's drawing. According to historians, the tablet was made in 2400 BC. The calendar was compiled before man's first organized scientific achievements, followed by the era of voyages of discovery, where once more the art of drawing was employed to depict the new world in the form of maps. One of the earliest maps of the world then known was that of Hecataeus, dating from 517 BC. The 18th century saw the invention of the steam engine and its use as a pumping apparatus for mines and collieries. A good 70 years later, the cylinder of the steam engine was connected through a crankshaft with a flywheel, and the reciprocating engine was born. The steam engine was then used to propel machinery to perform the work previously done by human hands. The production of woolen and cotton materials with machines in England gave rise to a big demand for engine building. The Industrial Revolution included the invention and adaptation of machinery as far as practically every industry was concerned. Not every simultaneously, but gradually over a period in which one industry depended on another, and everywhere the steam engine was used to propel collections of new machinery in factories. The first efforts to depict industrial objects with suitable dimensions for use in the manufacture of spare parts were based on three-dimensional drawings, but as the drawings became more complex, it became increasingly difficult to add adequate and distinct measurements to such a three-dimensional representation. The necessity for some other more convenient forms of representation arose. The first forms of orthographical projection drawings are to be found in the shipbuilding of wooden frigates and other men of war in England. Such drawings of warships are preserved in the National Maritime Museum in Greenwich in England. Certain details are presented according to purely orthographical projection, but in addition, three-dimensional drawings of certain ship parts are mixed with purely orthographical elements. So Gaspard Monge's contribution to the drawing world. The first distinct definition of orthographical projection was formulated by the famous Frenchman Gaspard Monge in about 1795. Gaspard Monge, 1746 to 1818, started his career as a draftsman, subsequently became a mathematician, and achieving fame Inter alia as a professor of descriptive geometry at the École Polytechnique in Paris. He is the inventor of modern descriptive geometry, and his research in this respect contributed much to the techniques of contemporary engineering drawing. It is interesting to note that Monge's invention of the orthographical representation was stimulated by the demand for military equipment. Monge held the office of minister in the government of Napoleon Bonaparte and was asked by Napoleon to expedite the delivery of war materials by making drawings of the military requisites for distribution in France, which could be used for the manufacture of equipment. A prerequisite was that that drawings should be readily intelligible. The following questions cropped up during research into the form of such drawings. Can a three-dimensional object be portrayed accurately on a two-dimensional paper plane? Another question is, would such drawings be able to read and be understood universally? In consequence of these questions, Monge did three things. He defined orthographical viewpoints and projection, and rejected three-dimensional forms of drawing. This action by Monge demanded courage because the mixture of orthographical and three-dimensional drawings had already gained popularity. Monge's view exerted great influence, also in countries beyond France. Typical of this influence is a drawing of a brickmaking machine made in England in about 1820. The art of making prints was still unknown at the time, and the original drawing had to serve as job drawing. It was pulled through a heavy-quality handmade drawing sheet in black ink, and different colors were used to differentiate between ferrous and non-ferrous parts. The method of orthographical projection is surprisingly modern, and sectional views were used freely. There is no reason for accepting that Monge specifically called his newly defined method of projection either first angle or third angle projection. He demonstrated his theory simply by depositing an object in a box of which the three sides had been removed. Subsequently, he showed how the object could be viewed orthographically from three different directions and then be projected in the sides of the box behind the object to show the three views in perfect light with one another when the sides are hinged back to form one plane. From this description, it could become clear that Monge was engaged in demonstration of first-angle orthographical projection as it is known today. With the exception of Holland, the whole industrial world of 1850 employed first-angle orthographic projection. So fun fact, did you know? For reasons unknown to us, Holland stuck to third-angle projection, and thus was the expectation at that time. So it has already been mentioned that orthographical projection replaced the three-dimensional single views, and that orthographical projection had been generally accepted. This switchover also had its disadvantages. With the increasing use of orthographical conceptions, the production of three-dimensional representation gradually fell into disuse. Examples of orthographic projection. Okay, so when some situation or other arose which necessitated a large and urgent demand for functional parts, particularly during times of war, the inability of unskilled labor to interpret orthographical projection was a definite obstacle in the manufacturing process, where drawings are the medium of instruction. Manufacturers were also compelled to add, together with the orthographical representations with dimensions, a three-dimensional picture of the drawing on each object, in order to show the form at one glance. Mention has already been made of the spread of the method of orthographical projection to countries outside France, and it may freely be assumed that drawings were indispensable for the industrial development of these countries. But did you know, one of the main features of industrialization at the beginning of the 20th century was the necessity for standardization, experienced by numerous industries. The British Engineering Standards Association was established in England in 1901, and in South Africa, an investigation into suitable local standards was recommended by the Transvaal Chamber of Mines in 1905, only 4 years later. A feature of all research by different committees in various countries is the role drawings played in the interpretation of the shape and size of the proposed standard objects. In England, for example, standards were submitted to countries such as France, Germany, Spain, Holland, and Portugal. The basic projection of drawing had the result that no problems arose with the interpretation of the contents of the drawing. So what are the personal attributes of draftspersons? So the draftsperson should have certain essential personal attributes and problem-solving ability. The following are the personal attributes required for draftspersons. Must be methodical and able to work accurately, neatly, tidily, and logically. Must be able to communicate verbally and in writing with all levels, from top management to shop floor workers. Must be able to use measuring instruments. Have a functional knowledge of his field. Be able to visualize shapes and sizes in 3 dimensions. Think about it. If you have good problem-solving abilities, which are necessary for draftsmanship, one must have the ability to apply one's knowledge to arrive at acceptable solutions to problems. So, if we look at the drawing office and what you might need in the drawing office, there are a few things that we can talk about. Drawing offices and the means of producing drawings existed in industry from the time that man first started to invent and produce such things as housing, boats, and simple wooden machinery. Since that time, it was realized that for a drawing to be produced, it was necessary to have a person who could transpose the information given to him by an engineer and produce a drawing which the tradesman could use to produce or build whatever the customer required. So, this procedure has remained exactly the same, that engineering itself has become very much more complex, and therefore requires many more draftspersons. The drawing office, therefore, can be considered an extremely important link between the customer, the engineer, and the final product. In short, modern industry cannot perform without draftspersons. Communication within the drawing office. The drawings and effects are simply the most accurate and cost-effective method of transmitting engineering information throughout industry. If you were to try and describe how to construct even the simplest article by means of words alone, it would take many hours of painstaking work, with no guarantee that the final product would be exactly what was required. As an example, if 3 people were asked to describe exactly the same article by means of words, it is unlikely that the end product would be the same in each case, and the cost in that time would be prohibitive. However, if 3 draftspersons were to draw that product by any one of the various ways of producing a drawing, not only would the process be much quicker, but the end products would be exactly the same. Thus, the production and use of drawings will always remain the prime method of communicating technical information throughout industry. Modern technology in the drawing office. So in the drawing office, there are a few different technologies that can be made use of. Things like microfilming, computer-aided drafting, we might know it as CAD. We'll talk about large document scanning. We'll talk about commercial scanning. And which falls a part of computer graphics and large document scanning. There are plotters out there. And that's it. So, if we look at microfilming, because of the quantity of drawings produced, especially in large engineering companies, the storage of valuable drawings becomes a matter of some concern, primarily because of the storage space required, but also because of such things as keeping the drawings safe from fire, flooding. As a result, microfilming was introduced. Microfilming is simply a matter of photographing a drawing and producing 35mm negative, which is then stored. A microfilm occupies less space than a full-size drawing. It can be reproduced more easily and be better protected from damage. However, because of the reduction process, it is imperative that the drawing line work and printing be of a high quality. Otherwise, the resulting prints will be unreadable and therefore useless. Then, the introduction of computer-aided drafting. Computer-aided drafting, rather known as CAD, is a comparatively recent innovation in drawing offices, but one which is becoming more and more common. I mean, think about it. The first and most important thing to understand about CAD is that it is not magic. It is only capable of producing a drawing to the standard of which the draftsperson is capable. The CAD system is only cost-effective if the type of work performed on it is carefully chosen. The situation is brought about simply because of the high cost associated with computers. The CAD terminal, however, can be invaluable when used on very repetitive drawings. Because any detail drawn once can be repeated as many times as you wish, thereby relieving the draftsperson of the more tedious work and saving time, CAD is also very useful for line diagrams, both electrical and mechanical, and especially pipework drawings, where the pipe runs are modeled in 3D, resulting in almost automatic isometric diagrams and bills of material. CAD can also be used for electronic transmission and storage of drawings, the storage being even better than microfilm, because of time saving and reproduction quality. CAD terminals can in some instances also be directly attached to mills and NAVs, thus making production fully automatic. Large document scanning. There are 2 different areas where the value of scanning has been recognized and is very widely used. So, what is scanning? Before we get into anything, the word scanning means to gather together. The modem equivalent in the computer environment to capture the information electronically, in other words, transforming paper-based information into electronic digital data. Commercial applications, particularly financial institutions such as banking, insurance, building societies, and the world of desktop publishing and data processing. With computer graphics applications such as engineering and mapping, line maps, GIS, geological, satellite and imagery are some to name. Definition of GIS. So GIS is a geographic information system. It's a computer system for capturing, storing, checking, and displaying data related to positions on Earth's surface. GIS can show many kinds of data on one map. This enables people to more easily see, analyze, and understand patterns and relationships. So from large document scanning, you get commercial scanning. The commercial field is limited mainly to the scanning of very large volumes of textual data using small A4 size flatbed grayscale scanners. In general, the data is scanned into a computer system for storage and screen view-only purposes. Data processing facilities, however, require fast optical character recognition software to convert the scanned raster text to ASCII code. Desktop publishing is concerned mostly with very high quality color scanning, which requires particular hardware and software technology. Commercial scanning is a branch of scanning that has many specialized features. There is little direct overlap with the engineering and mapping arena, and the subject will not be considered any further. Computer, graphics, and large document scanning. The CAD environment is concerned with document sizes up to A0, hence the name large document. And there are 3 steps to this process. There's input, where we scan the paper. We process it. So the scanned paper gets processed to the computer storage and is processed in terms of scanned data. And what you get is the output, which is a plotted paper. So the need in engineering and mapping is to convert the paper documents into an electronic form that can be easily stored, archived, accessed, or retrieved and processed, edited, and or revised. Finally, we need to plot the information using a computer system. Paper plot output. How does the scanner work? Very briefly, the document is placed so that it can be scanned by a light source. The intensity of light reflected from the surface of paper is modified by any markings on paper. These could be drafting lines and circles on a drawing with text and a stain or two on an aged document, or perhaps an aerial photograph, and so on. On a pinch roll scanner, the reflected light is directed to a transducer, typically a CCD, via either a set of high-quality lenses or optical glass fibers. So, before we get further into it, what is the definition of a CCD? A charge-coupled service, CCD, is a device for the movement of electrical charge, usually from within the device to an area where the charge can be manipulated. For example, conversion into a digital value. This is achieved by shifting the signals between stages within the device one at a time. So, the charge-coupled device converts the light rays it receives into electronic or bit data. If the scanner is limited to producing only black and white images, then each picture element seen by the charge-coupled device is represented by 1 bit. The output from the scanner appears on the computer screen as an image made up of black and white pixels. Of course, only the black pixels are visible on the white screen. So what determines the resolution of scanned data? Here we could ask the question, how small are the pixels? Resolution is defined as dots, pixels per inch, or DPI, and should always be stated in terms of true machine resolution. For example, consider a black and white fiber optic pinch roll scanner that has 20,000 optical fiber ends and distributed across the document into a slot of 1 meter width. Now, 10,000 optical fibers are used to deliver light to the document and 10,000 to return the reflected light to the charge-coupled device. By calculation, that gives 10 fibers per millimeter, 10 pixels per millimeter. The true resolution of the scanner would be 254 dpi. In metric measure, it would be 100 dots per centimeter, i.e., true pixel size would be 0.1 millimeters by 1 millimeter. By increasing the resolution, the quality of the screen image can be greatly improved. This is done by interpolation. Increasing the scan resolution to, say, 500 dpi gives a pixel size of approximately 0.05 millimeters and 0.05 millimeters. Interpolation, however, does not add to the information captured by the scanner. So, what is interpolation? Interpolation. In the mathematical field of numerical analysis, interpolation is a method of constructing new data points within the range of a discrete set of known data points. It simply enhances the quality appearance of the raster image. The image file size increases quite dramatically when the scan resolution is increased, which makes manipulation of the data more difficult.